Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, dear students. Welcome back to this TV Learning Series program. I'm teacher Patrick, and I'll be with the Senior 3 Chemistry class, and we look at Unit 5, which is rate of reactions. And our lesson today will also only be talking about the introduction to measuring rates of reactions. And by the end of the lesson, we'll be able to explain how rates of reactions are measured, and then we'll explain how the results obtained are graphically interpreted or analyzed. So that is our lesson of today. And I would like to urge you to pay attention and be with us. We'll be together in this lesson. But first of all, I just want to tell you that the rates of the reactions are very important, especially in real-life situations, because, for example, if you have an industry and you're producing some products, you need the products to be produced at a faster rate, and that's how the industry would be more economically viable and increasing even the costs and even the revenues. So usually some reactions are very slow, and the reactions that we encounter in everyday life, some of them are very slow, others are very fast, others even take days to occur. An example of the slow reaction I can give is the rusting. If you remember what we mean by the rusting. Rusting is one of the examples of the reactions that take place slowly. This is a knife, and I have just picked it outside here. If you look at it, you see it has changed the color. So the rusting usually destroys the metals. And that is the iron 3 oxide, the hydrated iron 3 oxide, that is the coating that metal of this that is making this knife. So rusting takes place slowly. It is one of the reactions that we encounter in everyday life that takes place very slowly. There are some reactions, even like fermentation. Fermentation of the alcohol, that reaction also takes even days. You can even mention even during the bakery when they are making bread, they have to add the sodium hydrogen carbonate, which is the baking powder that increases the size of the bread when it decomposes and produces the carbon dioxide gas, and then increases the size of the bread. That reaction does not take place very fast. So that is why sometimes even heating has to be employed during the baking process. So there are some of the reactions that take place very slowly. There are some other reactions. So we have mentioned rusting. We have mentioned the fermentation of alcohols. We have mentioned even like decomposition of sodium hydrogen carbonate in a baking process as some of the reactions that take place slowly. And so you can even mention some other reactions. You can think of other reactions that take place slowly. There are some other reactions that occur. They are even instantaneous. They take place very fast. And I'm just going to show you some of these reactions that take place instantaneously, or they occur very fast. So when we're talking about the rate, probably you can use the word either speed, which can be used interchangeably with the word rate, the speed of the reaction, how fast the reaction can go. And we look at the definition. So I just want to show you some of the reactions that that take place very fast. And some of those reactions are explosive. So I just want to show you one of the explosive reactions that occurs very fast. So I'll have potassium permanganate here. This is solid potassium permanganate. I'll just mix it with a very little concentrated sulfuric acid. This is potassium permanganate. So I'm just using this. This is clay because it resists too much heat, so it cannot easily break. That's why I'm not using either the beaker. So I'm just going to add very little of concentrated sulfuric acid. Very little concentrated sulfuric acid. Just mix them together. I hope it works out. Sometimes these reactions are I hope this is the alcohol. I'm just going to show you that one of the reactions that are explosive. So that's what happened. That reaction is very explosive, takes place very fast, immediately. That is one of the examples that I wanted to show you. And I have another example. So that is potassium permanganate. I just mixed it with the concentrated sulfuric acid, which oxidizes it to manganese 4 oxide, to manganese 7 oxide. And then that manganese 7 oxide, when it reacts with the alcohol, it explodes. So that is explosion reaction. It takes place very fast. And I just want also to show you another reaction. We have calcium metal. Calcium metal, so I just want to react this one with the very little dilute sodium hydrochloric acid. So these are calcium granules, not powder. So I will add dilute hydrochloric acid, and then you'll see what happens with dilute hydrochloric acid. So that is the reaction. This reaction takes place very fast, and it involves even the evolution of the gas. So the hydrogen gas is being produced. So you see the bubbling, the effervescence that comes out is because of the gas that is coming out. So you have, so we're looking at that was calcium, and it reacts with hydrochloric acid to produce the calcium chloride and the hydrogen gas, which is produced. So that is one of other reactions that take place fast. There are some other reactions which occur very fast. As I said earlier on, that some reactions go slowly, others go very fast. Sometimes they take days, they may even take years. So another reaction that I just want to show you is sodium. I have sodium metal here. Do I have sodium metal? Yes, I have it here. This sodium metal with the water. This is a familiar reaction. So we'll have the sodium metal. As I said, sodium is stored under paraffin. You remember last time we talked about this one, why the sodium is stored under paraffin. This is the sodium metal. So I will just put it in water. This is the water. Oh, sorry. So I'll get a small piece of the sodium metal, and I cut it. When you look at the sodium metal, it is very soft and shiny. That is one of the characteristics of the metals, the shininess. But the shininess disappears. When you look at it properly, the shininess disappears because it is exposed to air. It is very reactive. So in air, it reacts to form the oxide. So that is why the shininess disappears. And as I said earlier, you have to put it back in paraffin because to avoid the reaction with air. So this is the small piece of the sodium metal. And you will have to just check on what is happening. The reaction is also takes place fast. So that is the sodium metal. It is reacting with water. And this reaction is also, it is vigorous. It even catches fire depending on the size of the metal that has been used. And then reacts with the water to form the sodium hydroxide and the hydrogen gas. So we have even the sodium plus the water. As these are some of the examples I'm giving that takes place very fast, and then this forms sodium hydroxide plus the hydrogen gas. So it disappears with time. So maybe another reaction that I just wanted to show you is the reaction. This is a magnesium ribbon. I'm just showing you some of the reactions that takes place fast. And we have seen some reactions that move slowly and takes some time. So we're having magnesium ribbon, and we're just going to put it on fire. This is the metal. So we're just going to see what happens as we burn this metal. So if we put it on fire, our magnesium ribbon, what happens? So this is the magnesium ribbon. So not all other metals will catch fire in the same way as the magnesium does. So when you look at the magnesium ribbon burning, it won't catch fire like as we have. This is also a metal. So this reaction is also taking place fast. So it is not that all the metals can easily catch fire. This is a metal as well. This metal doesn't catch fire as magnesium does. This is magnesium ribbon. So it means that magnesium burns in oxygen at a faster rate compared to other metals. Even sodium does with the fire or with heat, and the reaction takes place faster. So those are some of the reactions that take place either in laboratories or either in real life situations that are very fast and very slow. So we have also seen magnesium reacting with oxygen to give magnesium oxide. Remember the explosion reaction. There are so many other explosion reactions, but the explosion reactions are also dangerous to carry out. So we have to make sure we avoid those explosion experiments as much as possible. Where we had potassium permanganate, said we have potassium permanganate was reacting with the concentrated sulfuric acid, and then plus ethanol. That reaction explodes as we have seen. Now, let's go to the rate of the reactions. How fast are these reactions? When we talk about the rate, what do we mean? So the rate of the reaction tells us how rapidly the products are formed or are made from the reactants. We had the reactants. We have calcium, we have hydrochloric acid, these are reactants. We have sodium, and how fast are the products formed? The products that are formed is either the evolution of the gases that we are seeing or any other product. So how fast do the products form from the reactants? So usually the rate of the reaction is given by the amount of reactants used. That's how we can measure the rate of the reaction. So we need to know the amount of reactants used in a given time. So that's why the amount of reactants used per unit time. Or we can even measure the rate as the amount of products made or formed in a given time. The given time can be either in minutes, can be in, you remember we have said, some reactions take long, others are very slow. So if for those reactions that take long, then that means the amount of products either per day or per minute or per year. Then we look at the measuring the rate of reaction. Now we have reactions that are taking place. Calcium and HCl producing the hydrogen gas. Now if it is producing the hydrogen gas, we can measure the volume of the gas. That is the volume of the product. Remember we said either the amount of product over a given time. So we have the hydrogen, the volume of the gas produced at certain time intervals. So if you have the zinc granules reacting with sulfuric acid or hydrochloric acid, they will produce the gas. Now, if they produce the gas, if you connect the syringe, then you can measure the time after 5 seconds. So after every 5 seconds, you record the volume of the gas that is produced here by this reaction. So that is at regular intervals. It has to be regular, either 5 seconds or 10 seconds, but the reaction has to be regular. That is number one. That is one way of how the rate of the reaction can be used. Using the product that has been produced, either the volume of the gas that is produced. Measuring the decrease in mass of the reactants. So if we had calcium and the hydrochloric acid, so we can also measure the decrease in mass of this calcium. That means after 5 seconds, we record the mass of calcium that remains. After another 5 seconds, we also record the mass of calcium that is produced. This is an example. Calcium carbonate with this will produce carbon dioxide. So any other reaction that produces the gas can also be used. So that is measuring either the mass of calcium carbonate that remains after regular intervals. Number 3 is measuring the time taken for the color change. I hope we'll look at this one later on. The color change, when sodium thiosulfate reacts with hydrochloric acid, it produces the sulfur. The sulfur is produced as a precipitate, and it is colored, sulfur is yellow. So how long does the sulfur, how long does it take for the sulfur to form when sodium thiosulfate and hydrochloric acid is used? So we are using the color change in that sense. So how do we interpret these results? By the rate, we use rate graphs. If we measure the amount of product formed, you remember we are measuring the amount of hydrogen formed at regular intervals, then versus, that is the time, then the results will look like this. So this is how the volume of the gas produced and the time. So you see, this is how the graph will go. So the gradient shows the rate of the reaction. This gradient here, it is showing the rate of the reaction. It is initially steep. When you look at this, it is moving like this. What does that mean? It's because the reaction is faster at the start. Even when you are looking at the reactions here that we are talking about, you would see the reaction starts very fast and it goes on slowing down. So this is what happens. Then the rate slows down towards the end. It is slowing down as reactants are used up. The gradient gets less steep. This is what we are talking about. At this level here, there is no more reactants. So all the reactants have been used up and there is no more gas produced. So that is, eventually the curve becomes flat and the reaction finishes. So at this level, the reaction has finished, or the reactants have been completely used up. Number two, we are using the amount of product. We can measure the amount of reactants as well, used up, or versus time. The reactants will look like this. So this is the graph that we have to get. Mass of the reactants, we said measure the mass after certain intervals of time. Initially, the gradient is still steep when you start at, this is at the beginning. So this is very steep, and then it curves, it flattens off. The curve becomes flat when the reaction stops, because the reactant has been completely used. The same reasoning that we are using here. So how do you compare? Note, the rate can also be measured in moles per second. Here, look at this. You can measure the rate, the speed of the reaction here, at any point here, by measuring the volume of the gas, recording the volume of the gas, and taking the change in time. That is the gradient at any point here, because the gradient here is 0. So at any point here, you will have the change in time, change in volume of the gas over change in time, which will be cubic centimeters cubed per second. How much of the gas is produced in 1 second? So look at these graphs. You have 3 graphs. We are just comparing, assuming the graphs are of this form. Which reaction is faster, blue or green reaction? So you have, this is blue, this is green. So which reaction do you think is faster than the other? This reaction here is faster than this. These reactions are the same, only that they are taking place at different conditions. How do you know these reactions are taking place at different conditions? Because they finish off, the reactions end at the same time. So they are leveling off at the same time. So that means these reactions, this blue one and the green one, are the same, only that these reactions could be taking place at different conditions, either of temperature or any other condition, as we'll talk about these conditions later on. So which reaction finishes faster? So when you look at, this is somehow obvious, when you look at this reaction, as this one is trying to move, so this reaction is finishing faster than this one. And of course, this one is the one that finishes least. Which two curves could be the same reaction happening? I think I've talked about this one before, because I've said these two are the same, of the same reaction, but occurring at different temperature. And different temperature means either low temperature or higher temperature. The lower the curve, the lower the temperature, and the higher the curve, the higher the temperature. So that is how we can measure the rates of the reaction by using either the reactant, which is the reactant that is used up, or the product that is formed in the reaction. So the product that is formed can be either the gas, and if it is a gas, in that case, you have to measure the volume of the gas at regular intervals of time. Either, I've said, the regular intervals can be either 5 seconds or can be 10 seconds. Maybe 5 seconds may be a very short time, but you can take 5 or 10 seconds and you record the volume of the gas every after 10 seconds, and then you will come up with the data. Now, when you come up with the data, we said that the data can be analyzed by using the graphical method. And that is either one of them, that is here we are measuring the products, the volume of the gas produced, and here we are measuring the volume, the mass of the reactant that is used up. And you remember we have said even the curve as the gradient, the rate can be determined at any point on this curve by determining the slope or the gradient, which would be the change in y over change in x, depending on what you are. So this one would be change in mass over change in time. This is change in volume over change in time. So you can get the rate at any point of the curve. I hope this is what we are supposed to look at today. But before I leave, I would want you to look at a simple homework that I've left with you, which is describe different methods that you can use to determine the rate of reaction. Draw a sketch graph to show how the reaction proceeds. Explain the shape of the graph at each point. You explain what happens depending on the shape. Thank you so much for watching and listening. Hope to be together in the next lesson. And the next lesson will be talking about the factors that affect the rates of the reaction. See you again. Bye-bye.